In today's video, I'm going to give you an intuitive explanation of simple harmonic motion. We say that an object is experiencing simple harmonic motion when its position oscillates around a given point, like a spring. The motion of such an object can be visualized using a spinning circle and a point. Let's draw a horizontal line that's stuck to this point. As you can see, the vertical motion of this line is a reciprocal motion, or a simple harmonic motion. This visualization looks very similar to the Scotch yoke mechanism, which you can see on the right, which converts reciprocal motion into circular motion. Oftentimes, we'll use the symbol omega to represent the angular velocity of the underlying circle which forms this simple harmonic motion. In this case, omega would be 90 degrees per second, or pi over 2 radians per second. The displacement of the object can be described using a sine wave, as seen by turning the line into a paintbrush. In mathematics, the sine of an angle is just the vertical displacement of this point when the circle has been rotated by that angle, assuming the point starts off at the right of the circle. Another system which experiences simple harmonic motion is a pendulum. I was always confused about this system because I thought omega in simple harmonic motion represented the angular velocity of the pendulum, but it doesn't. Rather, omega represents the angular velocity of the circle underlying this motion, as seen on the previous slide. This angular velocity is more of an abstract concept. The angles or the angular velocities of the pendulum and the simple harmonic motion circle cannot be interchanged. If you need a variable for both of these, I strongly suggest you use different symbols. Simple harmonic motion is defined by the equation a equals minus omega squared x, where a is the acceleration of the object, x is its displacement from the origin point, and omega squared is some constant greater than 0. As you can see, the acceleration is proportional to the object's displacement, meaning that the further the object is away from its origin, the greater the acceleration back towards the origin. The acceleration is just the rate of change of velocity, and so the velocity slows down as it reaches its maximum displacement due to this acceleration in the opposite direction. Eventually, the velocity reverses and the object goes back towards the origin. There is zero acceleration when the object is at its center point, but its existing velocity is what causes it to continue moving. The maximum displacement may also be referred to as the amplitude A. Simple harmonic motion can also be described using the equation x equals a sine omega t, where x is the displacement, a is the amplitude, omega is the angular velocity of the circle underlying this motion, and t is time. This assumes x equals 0 when t equals 0, and if x equals a when t is 0, then sine should be replaced with cosine. The two equations for simple harmonic motion can be shown to be equivalent, which we will derive at the end of this video. We can easily calculate the period, which is the time it takes to complete one full oscillation, by dividing omega by the angle of one oscillation, which is 2 pi radians or 360 degrees. If you graph the sine wave, the period is just a horizontal distance between any two corresponding points on the graph, such as the peaks. The simple harmonic motion equation describes an object which oscillates back and forth indefinitely. In a closed system, this equation accurately represents such motion in the real world. The equation is compatible with the conservation laws we would expect in physics. Although this equation can be used to model physical objects, it can also express the change of any variable in mathematics. Rather than writing a for acceleration, we will write the rate of change of velocity v, which can be denoted using v and a dot. Rather than writing v for velocity, we can write the rate of change of displacement s, which can be denoted using s dot. Overall, we can rewrite acceleration using x double dot, but the two notations are equivalent. However, we can now replace x with any other variable such as y if the same rules of oscillation apply to that variable y. Here we implicitly refer to the rate of change with respect to time, but we can use more verbose notation to be explicit. Y dot becomes dy dt and y double dot becomes d2y dt squared. Here the number 2 means the second derivative or the second order of the rate of change of y, similar to how we had 2 dots above the y before. Here we write t for time because we are referring to the rate of change with respect to time. However, we can also look at the rate of change of y with respect to other variables such as x, not necessarily just the passing of time. So here is an equivalent equation to simple harmonic motion, but applied to two different variables x and y. Now let us derive the simple harmonic motion equation from the sine equation, which will require some understanding of calculus to follow along. This will show that the sine equation obeys simple harmonic motion. The use of a sine equation also necessitates certain starting conditions and initial displacement, which cannot be inferred from the simple harmonic motion equation directly. Okay, let's begin. Assume x is equal to sine omega t. Then, by applying the chain rule, and since the derivative of sine is cosine, we have dx dt equals omega cos omega t. Similarly, by applying the chain rule again, and since the derivative of cos is minus sine, we have d2x dt squared is equal to minus omega squared sine omega t. We can then sub in x for sine omega t to get d2x dt squared is equal to minus omega squared x, or a is equal to minus omega squared x, and we are done. You could use a similar approach to check if cos obeys simple harmonic motion, and even add in some variables to control starting conditions, such as cos omega minus phi plus c. You could also try to prove that Hooke's law in physics is an example of simple harmonic motion. Thank you for watching this video. If you enjoyed or learned something, I would highly appreciate it if you left a like and shared this video. If you want to support my work, consider becoming a Patreon supporter. Link is in the description. Stay subscribed so you don't miss out on future videos.